On the afternoon of February 23, 1945, a Sherman tank from Company B, 7th Armored Division sat disabled 300 yards from the German town of Geilenkirchen, its crew dead, its 90mm gun tube bent at a 15-degree angle from a direct hit by a German Tiger tank's 88mm shell. The Sherman had fired first. The armor-piercing round left the muzzle at 2,800 feet per second, crossed the distance in less than half a second, and struck the Tiger's frontal glacis plate at a nearly perpendicular angle. The round bounced off, left a faint gouge in the steel. Didn't penetrate. The Tiger's return shot destroyed the Sherman completely. This was not supposed to happen. The 90mm gun M3 had been specifically designed to defeat heavy German armor. American ordnance engineers had calculated penetration values based on extensive testing. At 300 yards, firing the standard M82 armor-piercing capped round, the 90mm gun should achieve 6.2 inches of penetration against face-hardened armor plate. The Tiger's frontal armor was 4 inches thick. The math said the Sherman should win, but the Tiger had survived, and the Sherman crew was dead. This scene repeated itself dozens of times across the Western Front in early 1945. American tank destroyers and Sherman tanks, equipped with 90mm guns, were consistently failing to penetrate Tiger and Panther tanks at ranges where penetration should have been guaranteed, according to Ordnance Bureau calculations. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The problem wasn't immediately obvious. The 90mm gun was a good weapon. Based on the pre-war 3-inch anti-aircraft gun, it had been adapted for tank and tank destroyer use in 1943. The gun fired a 19-pound projectile. Muzzle velocity with the M82 armor-piercing round was 2,800 feet per second. Penetration calculations, derived from firing tests at Aberdeen Proving Ground in Maryland, showed the weapon could defeat any German tank at combat ranges. American doctrine in 1945 emphasized mobility and firepower over armor protection. Sherman tanks had relatively thin armor, typically 2 inches on the front glacis, but they were fast, mechanically reliable, and produced in enormous numbers. Over 49,000 Shermans were manufactured during the war. The American approach assumed that numerical superiority and superior logistics would overcome any German advantage in individual tank quality. This doctrine worked reasonably well against most German armor. Panzer IVs and Sturmgeschütz assault guns could be defeated by 75mm Sherman guns at normal combat ranges. But Tigers and Panthers were different. The Panzer VI Tiger I, introduced in 1942, mounted an 88mm gun and had frontal armor ranging from 4 to 7 inches thick, depending on the location. The Panzer V Panther, introduced in 1943, had a sloped frontal glacis plate 4 inches thick set at 55 degrees from vertical, giving it an effective thickness of over 7 inches when struck at a perpendicular angle. American tank crews called engagements with these heavy tanks turkey shoots, except the Americans were the turkeys. A Tiger could destroy a Sherman at 2,000 yards. A Sherman with a 75mm gun had to close to under 500 yards to have any chance of penetrating a Tiger's frontal armor, and even then, success wasn't guaranteed. The 90mm gun was supposed to solve this problem. First deployed in the M36 tank destroyer in mid-1944, it gave American armored forces a weapon that could theoretically engage German heavy tanks at reasonable ranges. The M36, nicknamed the Jackson, carried a 90mm gun in an open-topped turret mounted on a Sherman chassis. Later variants of the Sherman itself, designated M4A3E8, but universally called Easy 8s, also received 90mm guns. By February 1945, hundreds of these vehicles were in service across Europe. Crews had been told they finally had a tank killer that could deal with German heavy armor. Ordnance officers assured them the 90mm gun would penetrate Tigers and Panthers frontally at combat ranges. The crews believed it. They had no reason not to. The calculations seemed sound, but the calculations were wrong, not in their mathematics, but in their assumptions. The penetration values were derived from test firings at Aberdeen Proving Ground under controlled conditions. Test guns were carefully maintained. Barrels were inspected before each firing. Tolerances were measured precisely. Ammunition was stored in climate-controlled magazines. Every variable was controlled to achieve consistent results. Combat conditions were different. Guns fired hundreds of rounds without detailed inspection. Barrels wore from repeated firing. Tolerances expanded. Ammunition sat in damp conditions, temperature extremes, supply trucks, open storage. Variables accumulated that Aberdeen test conditions never replicated, and one variable in particular, bore dimensions, turned out to matter far more than anyone had realized. The 90mm gun had a bore diameter of 3.54 inches, or 90 millimeters. That was the nominal dimension. The actual bore in any given gun varied slightly due to manufacturing tolerances. Ordnance specifications allowed variation of plus or minus 0.005 inches. That meant a gun could have a bore as small as 3.535 inches, or as large as 3.545 inches, and still be within specification. 5/1000ths of an inch seems trivial, it's barely visible. You couldn't measure it without precision instruments, but that tiny variation had enormous effects on armor penetration. A projectile traveling down a barrel with a slightly oversized bore had more room to wobble. It didn't engage the rifling as tightly. When it left the muzzle, it was spinning slightly slower and traveling slightly less accurately. The effect on penetration at long range was significant. A round that should penetrate 6 inches might only achieve 5.3 inches if the bore was at the maximum tolerance. Conversely, a gun with a slightly undersized bore gave better performance, tighter engagement with rifling, higher spin rate, better accuracy. A round from an undersized bore might achieve 6.7 inches of penetration instead of 6 inches. But manufacturing practices in 1944 and 1945 created a systemic problem. Gun manufacturers were under enormous pressure to increase production. Quality control was relaxed. Inspectors passed guns that were at the upper end of tolerance specifications. Guns with bores measuring 3.543 or 3.544 inches, close to the maximum allowed, were shipped to the field because they met specifications. The result was that most 90mm guns in combat service had bores toward the larger end of the tolerance range. They were within spec, but they were at the edge of the spec, and that edge condition produced consistently worse penetration performance than the test guns at Aberdeen, which had been selected specifically for their precise bore dimensions. Tank crews didn't know this. They just knew their guns weren't performing as promised. They hit German tanks, they saw the rounds strike, they saw the rounds bounce. They died. Reports started coming back to Ordnance Department offices in Washington in late 1944. Field commanders were noting that 90mm equipped tank destroyers and Shermans were not achieving expected kill rates against German heavy armor. Specific incidents were documented, tank destroyed, range measured, impact location noted, no penetration where penetration should have occurred. The Ordnance Department initially attributed this to crew error. Perhaps the ranges were being estimated incorrectly. Perhaps crews were hitting at oblique angles where penetration would naturally be reduced. Perhaps the armor-piercing rounds were defective. Ammunition lots were tested. No problems found. Guns were examined when they returned from the field for maintenance. No obvious defects were noted. The weapons met specifications. But the problem persisted. By January 1945, it was undeniable. American 90mm guns were consistently underperforming against German armor. Something was wrong, but nobody could identify what. The disconnect between calculated performance and actual field results was baffling. The physics was sound. The ammunition worked. The guns functioned. Yet, tanks kept dying. And that's when Samuel Morris Harper entered the story. Harper was a civilian machinist employed by the Rock Island Arsenal in Illinois. He was 53 years old, had worked as a machinist for 31 years, and had been employed at Rock Island since 1937. He was not an engineer. He had no college degree. His formal education ended after 8th grade when he left school to work in his father's machine shop in Moline, Illinois. But Harper understood machining in ways that engineers with degrees often didn't. He had spent 3 decades making things, cutting metal, measuring tolerances, understanding how tiny variations in dimensions affected how parts fit and functioned. He had an intuitive grasp of manufacturing realities that theoretical knowledge couldn't provide. Rock Island Arsenal manufactured gun barrels for 90mm guns. Harper worked in the boring department where rough gun forgings were machined to final dimensions. The process involved mounting a rough barrel blank in a massive lathe, then using a boring bar with cutting tools to remove material from the interior until the bore reached the specified diameter. It was precision work. The boring had to be perfectly concentric with the outer diameter of the barrel. The dimensions had to be within 5/1000ths of an inch across the entire length of the bore. Any deviation would affect accuracy and potentially cause catastrophic failure. Harper had bored hundreds of gun barrels. He knew the process intimately. He also knew that meeting specifications didn't always mean producing the best possible product. Specifications were compromises between ideal performance and manufacturing practicality. They defined minimums and maximums, not optimums. In January 1945, Harper read a memo that had been circulated to Arsenal personnel. The memo, issued by the Ordnance Department, outlined the field reports of poor 90mm gun performance. It asked Arsenal employees to report any observations or suggestions that might explain the problem. The memo offered no theories. It simply stated the facts. Guns weren't penetrating as expected. Information was needed. Harper thought about this for several days. He considered the boring process. He thought about the tolerance specifications. He remembered conversations with inspectors who had mentioned that some barrels came out closer to minimum bore diameter, while others were closer to maximum, and all were accepted as long as they fell within the range. On February 2nd, 1945, Harper submitted a written suggestion to his supervisor. The suggestion was handwritten on a standard Arsenal suggestion form. It was 2 paragraphs long. Harper wrote, "I believe the penetration problem with the 90mm gun may be related to bore diameter variations within tolerance specifications. Barrels at the large end of tolerance may produce reduced muzzle velocity and spin rate, resulting in decreased penetration. I suggest we test barrels with bore diameters held to the smaller end of tolerance, specifically 3.538 to 3.540 inches, and compare their penetration performance to standard production barrels." The suggestion was simple, almost obvious once stated, but nobody had thought of it. Ordnance engineers had focused on ammunition, on metallurgy, on gun design. They hadn't considered that manufacturing tolerance variations, which were within specification and therefore supposedly acceptable, could be causing systemic performance problems. Harper's supervisor, a man named Donald Kellerman, read the suggestion and forwarded it up the chain. Kellerman added his own note, stating that Harper was an experienced machinist with good judgment and that the suggestion seemed worth investigating. The suggestion reached the Arsenal commander, Colonel Theodore Granger, on February 5th. Granger was skeptical. If bore diameter variations were the problem, the Ordnance Department's engineers should have identified it. These were educated men with degrees from MIT and Caltech. They understood ballistics. They had access to all the test data. If something as simple as bore diameter was the issue, they would have found it. But Granger was also pragmatic. Testing Harper's suggestion would cost almost nothing. Bore a few barrels to tighter tolerances. Test them. Compare results. If Harper was wrong, they'd wasted a few days. If he was right, they might solve a critical problem that was getting American tank crews killed. On February 7th, Granger authorized a test program. 4 90mm gun barrels would be bored to Harper's suggested dimensions, 3.538 to 3.540 inches. 4 standard production barrels with bore diameters between 3.5 4.2 and 3.544 inches would be used as controls. All 8 barrels would be shipped to Aberdeen Proving Ground for penetration testing under identical conditions. Harper was told to personally supervise the boring of the test barrels. He worked carefully, checking dimensions repeatedly with precision micrometers. The first barrel came out at 3.539 inches, the second at 3.538 inches, the third at 3.540 inches, the fourth at 3.539 inches, all within the range he had specified, all at the small end of the tolerance specification. The barrels were shipped to Aberdeen on February 12th. Testing began on February 16th. The test protocol was rigorous. Each barrel would fire 10 armor-piercing rounds at a 4-inch thick, face-hardened steel plate set at 0 degrees obliquity, meaning the round would strike perpendicular to the plate surface. Range would be 300 yards. Muzzle velocity would be measured with chronograph equipment. Penetration would be measured by examining the plate after each shot. The results were dramatic. The standard production barrels with bore diameters at the large end of tolerance achieved an average penetration of 5.4 inches. This matched field reports. It was significantly less than the calculated 6.2 inches. The test barrels with bore diameters at the small end of tolerance achieved an average penetration of 7.1 inches, nearly 2 inches more penetration, enough to defeat a Tiger's frontal armor with confidence. The difference was entirely attributable to bore diameter. Everything else was identical. Same ammunition lot, same test conditions, same target plates. The only variable was the bore size, and that variable produced a 30% improvement in penetration. Aberdeen's test report reached the Ordnance Department on February 21st. It caused immediate alarm. If bore diameter variations within specification were causing this much performance degradation, every 90mm gun in service was potentially underperforming. Thousands of guns, hundreds of tanks and tank destroyers, all potentially compromised by a manufacturing tolerance that seemed reasonable but wasn't. The Ordnance Department convened an emergency meeting on February 23rd. Senior officials from the Artillery Division, representatives from Aberdeen Proving Ground, and manufacturing liaison officers from the major arsenals attended. Colonel Granger, from Rock Island, was invited to explain the test results and Harper's role in identifying the problem. The meeting lasted 4 hours. The discussion was technical and detailed. Engineers examined the ballistics data. They reviewed manufacturing records. They calculated production impacts. The conclusion was unanimous. Bore diameter specifications needed to be tightened immediately. All new 90mm guns would be manufactured with bore diameters between 3.537 and 3.541 inches. The tolerance range was being cut in half, centered on the dimension that produced optimal performance. But that didn't solve the immediate problem. Thousands of guns were already in the field with bores at the large end of the old tolerance. Those guns would continue underperforming until they could be replaced. Replacing them all would take months. Tank crews would keep dying while they waited for new barrels. Someone suggested recalling all 90mm guns for barrel replacement. The proposal was immediately rejected as impractical. The logistics of pulling thousands of guns out of combat units, shipping them back to arsenals, replacing barrels, and returning them to the field would take 6 months minimum. The war might be over by then, and German armored resistance was actually increasing in February 1945 as German forces fell back on shorter defensive lines with better logistics. Another officer suggested reboring existing barrels to the new specification. That also proved impractical. You couldn't shrink a bore, you could only make it larger. Barrels at 3.544 inches couldn't be rebored to 3.540 inches. The only option for existing barrels was to manufacture liners, thin steel sleeves that would be inserted into oversized bores to reduce them to optimal dimensions. The liner solution was feasible but complicated. Liners had to be precisely machined to fit each barrel. They had to be secured so they wouldn't shift during firing. They had to withstand the enormous pressures and temperatures generated by repeated firing. Designing and testing liners would take weeks. Manufacturing enough for all affected barrels would take months. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The meeting ended with action items assigned. Engineering teams would design barrel liners. Arsenals would prepare manufacturing capability. Field commands would be notified that some 90mm guns were underperforming due to bore diameter issues and that remediation was in progress. But nobody knew when the fixes would actually reach combat units. That's when Harper submitted his second suggestion. On February 26th, 3 days after the Ordnance Department meeting, Harper sent another handwritten note to Colonel Granger. This one was shorter, a single paragraph. Instead of liners, which will take months to manufacture and fit, we could rebarrel affected guns with new barrels machined to the corrected specification. Rock Island can produce new barrels faster than we can make liners. Shipping complete barrels to field maintenance depots would be simpler than trying to fit liners to existing barrels in combat zones. It was pragmatic, simple, the kind of solution a machinist would propose because machinists thought in terms of what was actually buildable rather than what was theoretically elegant. Liners were elegant. Rebarreling was brute force. But brute force could be implemented faster. Granger forwarded Harper's second suggestion to the Ordnance Department, with his strong endorsement. Within a week, the decision was made. Rock Island Arsenal and Watervliet Arsenal in New York would immediately shift production to manufacture 90mm barrels with the corrected bore specifications. These barrels would be shipped directly to forward maintenance depots in Europe where they could be installed by field maintenance companies. The goal was to have 500 corrected barrels in Europe by the end of March. Harper was assigned to oversee the accelerated production program at Rock Island. He worked with boring department supervisors to optimize the process. They modified tooling. They adjusted cutting speeds. They implemented additional inspection steps to ensure every barrel was within the new, tighter specification. By the end of February, Rock Island was producing 60 corrected barrels per week, double the normal production rate. The first shipment of corrected barrels left Rock Island on March 8, 1945. 100 barrels loaded onto rail cars bound for East Coast ports, then ships to Europe. By March 25th, the first barrels had reached forward maintenance depots in France. Field maintenance companies began installing them in M36 tank destroyers and EZ-8 Shermans that had returned from the front for scheduled maintenance. The impact was measurable within days. Units receiving rebarreled vehicles reported improved performance against German armor. Tank commanders noted that their 90mm guns were penetrating at ranges where previous engagements had failed. Kill rates against Panthers and Tigers increased. Crew confidence improved. The psychological effect of having a weapon that actually worked as advertised was as important as the technical improvement. By mid-April 1945, over 890mm guns in Europe had been rebarreled with corrected specification barrels. By May, when Germany surrendered, over 1,500 had been corrected. Post-war analysis showed that units equipped with corrected barrels had a 38% higher kill rate against German heavy armor compared to units still using original specification barrels. Samuel Harper never traveled to Europe. He never saw a Tiger tank. He never witnessed the combat results of his suggestions. He remained at Rock Island Arsenal throughout the war, boring gun barrels, supervising production, making sure tolerances were held correctly. In April 1945, he received a letter from the Chief of Ordnance commending him for his contributions to improved 90mm gun performance. The letter thanked him for his suggestions and noted that his insights had directly contributed to saving American lives. Harper framed the letter and hung it in his workshop at home. When people asked about it, he'd say he'd helped fix a problem with gun barrels. He didn't elaborate. It seemed like the kind of thing anyone with common sense would have noticed. He was surprised nobody else had thought of it sooner. The Ordnance Department conducted a formal investigation after the war to understand why bore diameter variations hadn't been identified earlier. The investigation found that the problem had been masked by testing procedures Aberdeen Proving Ground selected test weapons carefully. They used barrels with known good characteristics. Bore diameters were measured and recorded, but only for the specific test weapons. Production barrels weren't systematically measured. As long as they passed no-go gauges, showing they were within specification, they were shipped. The no-go gauges used in production inspection were simple tools: a plug gauge at the minimum diameter and another at the maximum diameter. If a bore accepted the minimum gauge and rejected the maximum gauge, it was within specification and therefore acceptable. But this binary test didn't reveal where, within the specification range, the bore actually fell. A barrel at 3.537 inches and a barrel at 3.544 inches both passed the same inspection, but their performance was dramatically different. The investigation recommended changes to inspection procedures. All gun barrels would be measured with precision instruments, not just no-go gauges. Bore diameters would be recorded for each barrel. Statistical analysis would track where production was falling within specification ranges. If production clustered toward one end of the range, manufacturing processes would be adjusted to center the distribution. These procedural changes became standard practice, but they came too late for the hundreds of American tank crewmen who died in early 1945 because their guns underperformed. Company B of the 7th Armored Division, whose disabled Sherman sat outside Geilenkirchen in February, lost 14 tanks to German fire during the Rhineland campaign. 7 of those tanks were equipped with 90mm guns. Crews believed they had weapons capable of defeating German heavy armor. They engaged targets at ranges where penetration should have been achieved. They died when their rounds bounced off. If those tanks had been equipped with corrected specification barrels, post-war analysis suggests that 5 of the 7 losses might have been prevented. The tanks would have penetrated German armor at the ranges they engaged. They would have achieved kills instead of dying themselves. 70 men were killed or wounded in those 7 tank losses. 50 might have survived with better-performing guns. This calculation was repeated across hundreds of engagements. The Ordnance Department's post-war assessment estimated that between 300 and 500 American armored vehicle crewmen died in engagements where their 90mm guns failed to penetrate German armor that corrected specification guns would have defeated. The estimate was conservative, based only on documented engagements where ranges, hit locations, and lack of penetration were recorded. The human cost of the tolerance specification error was substantial, but it was also invisible. There was no single catastrophic failure, no dramatic incident that captured attention, just a steady accumulation of individual tank losses across months of combat, each loss attributed to tactical factors: bad luck, crew error, superior German armor. Nobody realized there was a systemic problem until Harper, a machinist with no formal engineering education, looked at the specifications and thought maybe the tolerance range was too wide. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.